Hello and Assalamualaikum warahmatullahi wabarakatuh. Today, me and my team are going to talk about revolutionizing airspace, the role of composite materials in modern aircraft design. So, this is me and my team. I am Muhammad Arif Fitri bin Baharudin, and then we have Noor Hamiza Izati binti Muhammad Muin, and then we have Aisyah Najla binti Muhammad Rusdi. So this is the topic overview. We have introduction, background and history, examples and application, advances and innovation, benefits and advantages, challenges and limitation, future trends, and then finally the conclusion. To give you an introduction about our topic, the aerospace industry is undergoing a profound transformation driven by a pressing need for lighter, stronger, and more fuel-efficient aircraft. Composite materials, particularly carbon fiber reinforced polymers (CFRPs), alongside advanced metal and ceramic matrix composites, have emerged as game changers. These materials offer exceptional strength-to-weight ratios, design flexibility, corrosion resistance, and fatigue performance, enabling modern airframes like Boeing 787 and Airbus A350 to exceed efficiency benchmarks. Innovation in manufacturing, such as out-of-autoclave methods, thermoplastic composite, automated layouts, and additive techniques, are accelerating adoption while reducing production costs and cycle times. In tandem, intelligent composites infused with nanoparticles and smart sensing capabilities are enhancing damage tolerance and enabling embedded structural health monitoring. As the industries aim for greener flights and rapid scalability, composites play a central role in redefining aerostructures, sustainable propulsion, and next-generation aircraft systems.
Let me now go over the history and development of composite materials in the aircraft industry. Before the 1960s, composites were mostly used in non-structural parts such as cabin panels and interior. In the 1960s, fiberglass began to be used for helicopter rotor and small airplane components. This marked the start of using composite in secondary structures like rudders and spoilers. Moving into the 1970s, carbon fiber composites replaced fiberglass. This offered stronger and lighter parts. Helicopter also switched from metal to composite rotor blades. In the 1980s, composites were used in larger aircraft structure such as Boeing 737 stabilizer. They also started being used in wing and fuselage sections. By the 1990s, the Boeing 777 incorporated advanced composites in its tail and control surface. This innovation significantly reduced the aircraft weight, improving strength. And finally, from 2000 until now, modern aircraft like the Boeing 787 Dreamliner and the Airbus A380 are made of more than 50% composite materials. This improves fuel efficiency, corrosion resistance, and reduce maintenance needs. Going on to its application. In airframe structures, composites are used in parts like the fuselage, wings, tail, and control surface. Due to the height strength and lightweight, this material enhances fuel efficiency and overall flight performance. Composite were also used for engine components such as fan blades and coverings. This makes the engine lighter, which helps improve performance and reduce fuel use. And for the third one, composite also play an important role in the spacecraft and satellites. Since weight is a big concern in space missions, using lightweight materials helps to reduce launch costs and improve mission success. There are a few actual instances of airplanes that employ composite materials. To begin with, we have the Airbus A380. Approximately 22% of its structure is made from composite. These are mainly found in the center of wingbox, rudder, elevator, and rear fuselage. We also have the Boeing 787 Dreamliner as one of the most advanced aircraft in terms of composite usage. Around 50% of its structure is made from carbon fiber reinforced polymer (CFRP). These include parts like the wings, fuselage barrels, and the tail section. And for the third one, we have the Boeing 777 also makes significant use of composite, though not as much as the 787 Dreamliner. Composite are used in its floor beams, tail surface, and fairings.
For advances and innovations, first we had lightweight hybrid composites with metallic ceramics matrices in 2022. To enhance metal and ceramic matrix composites are being used in combination with CFRPs to improve fatigue resilience, corrosion resistance, and thermal performance in aircraft systems. Second, we have EMI shielding and morphing airframe structures from 2023 to 2024. The integration of MZ and carbon nanomaterials into composites enables morphing wing structures and EMI protected avionics, enhancing aerodynamic efficiency and electromagnetic reliability. So let's go on with smart composites with embedded sensors from the same 2023 to 2024. It is the development of composites featuring embedded piezoelectric fiber optic and carbon nanotube sensors enables real-time structural health monitoring (SHM), detecting microcracks and stress before failures occur. Then we have AI and machine learning driven SHM system 2024. Advancements in wireless SHM systems that integrate carbon nanotube sensors and AI-driven predictive algorithms now offer real-time condition assessment and yearly failure forecasting in CFRP structures. Composite materials offer numerous advantages and disadvantages in aircraft applications, primarily due to their high strength-to-weight ratio. This means they can provide the same greater structural strength as metals while significantly reducing overall weight, which improves fuel efficiency and extends flight range. Additionally, composites are highly resistant to corrosion, making them ideal for long-term use in harsh environmental conditions without the need for protective coatings. They also exhibit superior fatigue resistance as they do not develop stress cracks the same way metals do under repeated loading. One of the most significant benefits is the ability to tailor mechanical properties by orienting fibers in specific directions to strengthen critical load paths. Furthermore, composites can be molded into large, complex structures, reducing the number of joints and fasteners required, which enhances overall structural integrity and reduces assembly time. But they are expensive to produce due to the high cost of raw materials like carbon fiber and the need for specialized equipment such as autoclaves. Damage detection is challenging because composites can suffer from barely visible impact damage that requires advanced non-destructive testing methods to identify. Repairs are complex, time-consuming, and require skilled labor. Additionally, composites are sensitive to environmental factors such as moisture absorption and UV degradation, which can affect long-term performance. Their failure tends to be sudden and brittle with little warning before structural collapse. Recycling composites is also difficult, making them less environmentally friendly than metals. Overall, while composites offer performance advantages, they present significant challenges in cost, maintenance, and end-of-life disposal. Continue with future trends. Unlike traditional thermosets, thermoplastic composites are easier to reshape and recycle. They offer shorter manufacturing cycles and are more damage tolerant, making them ideal for future high-rate aircraft production. New technologies like AFP and ATL are making composite manufacturing faster and more precise. Out-of-autoclave processes avoid the need for expensive pressure chambers, enabling lower-cost, large-scale production. Next generation composites won't just be strong, but they will be smart too. Materials are being developed that can be sense damage, store energy, or conduct electricity, allowing for real-time monitoring and improved safety. Digital twins use embedded sensors in composites to create a real-time model of aircraft structure. This helps engineers to detect problems before failure, improving safety and reducing downtime. Incorporating nanomaterials like graphene and carbon nanotubes can solve issues like electrical insulation and impact weakness. These hybrid composites are also being studied for stealth and high-performance military aircraft. Urban air mobility (UAM) refers to a transportation system for people or cargo within urban environments, using electric or hybrid vertical takeoff and landing (eVTOL) aircraft or smaller airborne vehicles. It is to reduce traffic congestions and improve transportation efficiencies in cities. For UAVs are aircraft systems without an onboard human pilot, operated remotely or autonomously. They are commonly known as drones for performing tasks that are too dangerous, expensive, or difficult for manned aircraft. Many composites are no longer just about weight savings. They become intelligent, sustainable, and efficient, redefining what modern aircraft can do.
So, in conclusion, composite materials have profoundly reshaped the aerospace industry by enabling lighter, stronger, and more fuel-efficient aircraft, from carbon fiber reinforced polymers to smart thermoplastic composite with embedded sensors. These innovations have redefined how aircraft are designed, built, and maintained. While challenges such as high production costs, difficult repairs, and recycling limitation remains, ongoing research and technological advancements continue to expand the potential of composite in both commercial and military aviation. As the demand for sustainable and high-performance air travel grows, composite materials will remain at the core of next-generation aerospace engineering, driving the industry towards a smarter, greener, and more efficient future.